All right, good morning, everybody. As Howard said, my name is Peter Loezos, and I lead the services group for CPFD located in Houston, Texas. And so today I'm going to talk to you about turnaround risk reduction through FCCU simulation applied to the modeling of stripper, spent catalyst standpipes, regenerator, and riser flows. So let me start by giving you a brief introduction to CPFD. So CPFD provides engineering services and software that support root cause analysis of unit underperformance, risk reduction through virtual testing, the identification of optimization opportunities, and finally, technology development and scale up. So although I'm going to be focusing on the FCC unit for most of this presentation, I do want to note that our services and software do have a broad application across the refining, petrochemical, renewable, and energy industries. Let me do this. All right. So before I go into the specific focus area and case studies, what I want to do is touch on the various areas of the FCC unit and talk to you about some of the CFD specific deliverables. So starting with the risers. So in the riser, we study the feed zone. That includes feed penetration, vaporization, and dispersion. In the upper riser, we look at catalyst holdup and back mixing, as well as catalyst contacting efficiency, and how all this impacts conversion and selectivity. We also look at strippers, withdrawal wells, and spent catalyst transfer. So in the stripper, we study stripping efficiency, channeling, fluidization and withdrawal, and finally aeration and pressure build within the standpipe. And finally, one of our traditional areas, regenerators and internals. So we look at spent catalyst inlet design, mixing and catalyst regeneration within the regenerator bed, afterburn, catalyst losses, fluidization and withdrawal, and finally aeration and pressure build within the regenerator standpipe. Now, although I'm not going to focus on this today, we also do study the RTD, riser termination devices, and cyclone systems. So let me touch on some fluidization characteristics of the stripper, standpipe, regenerator, and the riser. So what I want to note is these operate in very different fluidization regimes. So in the riser, you have dilute phase flows, while in the stripper and the standpipe, you have relatively dense phase flows. And let me turn your attention to this plot on the right. I think most of you are familiar with this. This is a typical fluidization diagram for an FCC catalyst, where we're plotting void fraction versus superficial velocity. And we're plotting this over several different fluidization regimes. So if you look at the high velocity end of the plot, around 10 meters per second, we have the fast fluidization regime, and this is where the riser operates. And so typically here we have relatively low solid densities of about 5 cubic feet or less, especially in the upper riser. And the holdup in the riser is going to be proportional to the circulation rate. So if we look at the very other end of this plot, the low velocity end, we have the bubbling regime. And these are dense phase flows where the stripper and the standpipe operate. Densities here can be 40 pounds per cubic foot or higher, especially in the stripper. Now, intermediate between these two, we have what we call the turbulent bed regime, and this is where the regenerator operates roughly at between half and 1 meter per second. So what I want to note here is that the performance characteristics in these fluidization regimes are dominated by very different physical drivers. And CFD is going to be most effective when coupled with a solid understanding of these basic fluidization principles. So now I'm going to transition and talk to you about our first focus area, which is the stripper and the spent catalyst standpipe. And again, these are dense phase flows. And here the performance is going to be dominated by enduring contact between particles. And the dominant feature here, what's critical to capture when modeling these flows, are the bubbling and de-aeration characteristics. And to support this, we released a new feature in 2019 This is a new solid stress feature that determines what we call this window of stable expansion. We're going to touch on this for the next few slides, but what that window of stable expansion is, it's really the extent by which the catalyst can expand upon fluidization before bubbling. Again, a critical feature. So let me talk about stripper and standpipe performance. As most of you know, ECAT, PSD, particle size distribution, will have a significant impact on the FCCU or CFB circulating fluidized bed operation. So coarse or low fines content ECAT can lead to unstable circulation and potentially operational interruption. So these circulation constraints associated with a coarse ECAT, they can manifest itself in the following ways. So first, you can get rapid defluidization below the stripping steam ring, and you can begin to develop stagnant or defluidized zones at the base of the stripper and the standpipe entry. So from there, the catalyst can break off, causing erratic flow. And once that catalyst is in the standpipe, it'll have, if it's a coarse ECAT, it'll have a very narrow window of stable expansion. What that means, it's going to be very sensitive to both over-aeration and under-aeration. So especially if you over-aerate it, you can have larger and faster rising bubbles. That'll cause a flow restriction, and all this is going to lead to low standpipe and slide valve DP and unstable circulation. So CFD has been used to simulate stripper and standpipe flows. An example of that is given right here. This was a paper by Ray Coco and Ted Knowlton from PSRI back in 2017. So although CFD has been used to simulate stripper and riser flows, limited attempts in capturing the effects of PFD, these typically experienced of a refiner, have been considered. So here's a typical example. If you look at the plot at the top right, this could be a typical PSD shift experienced by a refiner. So we have the typical ECAT and the coarse ECAT. I'm plotting volume percent versus particle size. Typical ECAT, average particle size is roughly 80 microns, while the coarse ECAT, it's around 100. So what causes these PSD shifts? It could be loss of fines due to poor cyclone performance. The refiner could be using a coarse grade catalyst or additive, or you could be using a highly attrition resistant catalyst. And that's more common in chemicals applications where the cost of the catalyst is significantly higher than that of FCC CAT. So capturing these fluidization properties as a function of PSD are critical for dense phase flow applications. So where we have to capture the window of stable expansion and defluidization times. And to do this, we need an accurate representation of the particle phase stress, right? And these parameters can be extracted through simple experiments that we perform at CPFD. So if I draw your attention before leaving this slide to the plot at the bottom right, I think most of you are going to be familiar with this. This is called the Geldart diagram, and it classifies particles based on their fluidization properties. The FCC catalyst is a Geldart group A type of particle, which means it's very easy to fluidize. It has a nice window of expansion before it begins to bubble. Now, as you begin to coarsen that ECAT, or let's just say lose a portion of the fines, what happens is that group A particle starts to move towards this AB transition, and it begins to behave more like a group B particle. Group B particles, and Sand's an example of that, they bubble almost immediately upon fluidization, and they're generally much more challenging to circulate. So I'm going to give you an example of the fluidization, defluidization experiments that we perform at CPFD. What you're seeing here are experiments performed for a typical ECAT and a coarse ECAT. And the properties of the catalyst are the same ones you saw before. They're given here in this plot, with the typical ECAT having about an 80 micron average particle size, the coarse ECAT about 100. Okay. So what we do here is we have glass columns. These are approximately 4-inch in diameter. We'll fill the catalyst up to the rest state, which is this blue line right here. And what we'll do is we'll slowly and incrementally expand the catalyst right until bubbling occurs. And the kind of measurements that we get from this, we get bed height, as well as pressure drop, among others. So the blue arrow in this case will represent the rest height of the bed, while the red arrow will represent the fully expanded height before bubbling occurs. Right? So we wait a second here. Okay, we're slowly increasing the fluidization gas, it's air in this case, and at some point, you'll expand the bed and bubbling occurs. What you see, if you look at the typical ECAT versus coarse ECAT, is that typical ECAT will expand much more as compared to the coarse ECAT. So you get about a 30% or more expansion with the typical ECAT. The coarse FCC ECAT has about a 15% expansion. And so again, I want to draw your attention to the Geldart diagram below. As I mentioned before, the FCC catalyst, it's a group A type of particle, right? Nice window of expansion. As we begin to lose the fines or coarsen the catalyst inventory, you start to move to that A-B transition, right? And you get a much smaller window of stable expansion. Okay, so now let me focus on a case study. And in this case study, the Gulf Coast refiner was experiencing erratic circulation in their stripper and standpipe post-revamp. So although the revamp was generally successful, the circulation performance did fall short of expectations. And stable operation was only achieved by over-aerating the spent catalyst standpipe, and that resulted in low DP in the standpipe and across the spent catalyst plug valve. So I have two examples of this behavior on the right, two different plots. I'll only go through one of them. But in this plot, we're plotting stripper bed level, standpipe pressure build, plug valve opening, plug valve DP, and fluffing steam rate for several hours on stream. And what's going on here is the refiner's trying to reach the target DP across a plug valve, which is about 5 PSI or higher, by decreasing the fluffing steam flow rate to the target level. Now, as they're doing this, they're reducing the fluffing steam rate. The DP is increasing across the plug valve, right? At which point they do get a circulation interruption, and they have to increase the fluffing steam flow rate back up to the very high level that they were before, going back to the low DP across the plug valve, right? So the plot below says the same thing. I'm not going to go through it. So CPFD was approached to identify the root cause. So was it due to the stripper standpipe redesign and the associated fluffing steam and standpipe aeration rates, or was it due to the coarse ECAT resulting from excessive losses through the regenerator cyclones? So that was a question that we had to answer, and to do that, it was critical to quantitatively predict changes in the fluidization properties as a function of fines or PSD. So to summarize, the refiner needed low or designed fluffing steam rates, and that resulted in marginally acceptable DP, but erratic flow. Increasing the fluffing steam stabilized the flow, but resulted in very low DP across the standpipe and across the plug valve. And this low plug valve DP prevented their migration to their new safety system. Right, so let me talk a little more about the simulations. So simulations were performed to gain insight into the particle vapor hydrodynamics from the bottom of the stripper internals to the inlet of the standpipe. And again, we performed two base case simulations. So case one was with a typical ECAT PSD, and case two was with a coarse ECAT PSD. And so taken together, these two base cases would identify the root cause of poor circulation performance. In other words, was it due to the fact that they were circulating a coarse ECAT, or was there an inherent problem with the stripper and standpipe design? So before going into the simulation results, let me touch on the catalyst particle properties and the fluidization characteristics. So we performed typical fluidization and deaeration testing, where we compared the fluidization properties of the coarse ECAT against a typical FCC ECAT. And those results are summarized in the table below. If you look at the typical ECAD, that has an average particle size of about 80, the coarse ECAD closer to 100. If we look at the fines content, which is the 0 to 40 content, we have 4% fines in the typical ECAD with about 0.5% in the coarse ECAD. Now, looking at the fluidization properties, if you look at the UMB, velocity of minimum bubbling, versus UMF, velocity of minimum fluidization, that ratio is 3.57 for the typical ECAD and much lower for the coarse ECAD, about 1.9. And this window of stable expansion, this MSER that we were talking about, 1.31 for the typical ECAD, which means it could expand just over 30% above the rust height and about 15% for the coarse ECAD. So the results of the fluidization experiments that we performed are summarized in this table here. I won't go through this in detail, but I will highlight the values that we're getting for the typical ECAD. Again, 30% expansion at the point of bubbling, where the UMB was about 1/4 foot a second. If you look at the coarse ECAD, a much lower extent of expansion, 15%, and of course UMB there is significantly lower. So from experiments like these, we're able to extract what we call a normal stress or a compressive yield stress curve, and that's going to be unique to each one of the catalysts studied. Now, this is a direct input into Barracuda, which largely determines the fluidization properties that we see here. So let me go through some of the simulation results. What I'm plotting here is pressure versus time for 6 different positions in the standpipe. So we have 6 pressure taps located along the length of the standpipe for the coarse ECAD and a typical ECAD. So if you look at the coarse ECAD simulation has difficulty in achieving steady circulation at the desired air rate. So if you look at the pressure profile periodically, let's say about once every 30 seconds, what you'll see is a pressure bobble. This is a circulation interruption. And the only way we could stabilize flow was by significantly increasing the fluffing steam flow rate, right? And that's generally consistent with what they saw in the refinery. Now, if we look at the typical ECAD exhibits a much smoother pressure profile over the domain with a slightly greater pressure build versus the coarse ECAD simulation. So if we look at the simulation results, the 2 animations here, we have coarse ECAD and typical ECAD for a vertical cross section in the riser. And what I'm plotting here, what I'm showing here is particle volume fraction. So if you look at the coarse ECAD, what you'll see is that catalyst begins to defluidize almost immediately below the stripping steam ring. And that defluidized zone, that stagnant zone, builds up almost to the height of the steam ring, stripping steam ring. If you look at the typical ECAD, that catalyst remains well fluidized down to the bottom of the stripper and entering the standpipe, so much smoother flow. So to summarize the simulation results, with the coarse ECAD, we see a large defluidized catalyst zone apparent in the elliptical head extending to the main stripping steam ring. Additionally, the fluffing steam ring has, we see poor penetration into this defluidized zone, so we're really not able to break it up even with the higher fluffing steam rates. If you look at the typical ECAD, what you will see here is you will have longer deaeration times, right, allowing for a smoother transition and well-fluidized catalyst at the inlet of the spent catalyst standpipe. So based on these simulations, we determined that the root cause of poor circulation was due to the coarse ECAD, not the inherent stripper standpipe design. So let me end this focus area with conclusions and path forward. Our simulation results provide key insight into the fluidization characteristics of catalysts in the stripper transition to the spent catalyst standpipe. And this performance was well captured by parameters extracted through simple fluidization experiments. So where's the refiner today? The refiner is conducting additional simulation efforts with CPFD to assist in identifying the scope of the next turnaround. So they're looking at several different design options, redesign options for the stripper. So the first is a secondary fluffing ring. They're also looking at increasing the standpipe penetration into the stripper vessel. So the idea here is to potentially draw from a better fluidized zone. They're also looking at a larger diameter single fluffing steam ring. So the idea here is to get that fluffing steam ring further into this defluidized zone of catalyst and potentially break it up. They're looking at lowering the height of the main stripping steam distributor lower, and that's to compensate for the more rapid defluidization times of the core CCAT. And finally, we'll touch on this in a few moments, but or actually in the next slide, but they're looking at also revamping the regenerative cyclones and internals to maintain the fines inventory in the ECAT. And so before I leave this slide, I'll just draw your attention to these two plots on the right. This is circulation rate, catalyst flow versus time for the base case, which is case 1, and one of the design cases. I can't tell you specifically which one that is. But as you saw before for case 1, periodically, in this particular case, it's about every 20 seconds or so, you'll actually see a circulation interruption. Where if you look at case 4, which is one of the redesign options, we actually see very stable flow. So let me shift now and touch on one of our traditional focus areas, and that is the FCC regenerator. So what are some typical regenerator objectives? So we look at spent cat distribution and combustion air bypassing in the main regenerator bed. We look at CO and O2 breakthrough and the resulting afterburn, among other objectives. So let me highlight a typical regenerator case study that we performed using Barracuda Virtual Reactor, and that is shown here on the right. And in this particular case, the refiner was experiencing significant afterburn in the dilute phase of the FCC regenerator, and they came to CPFD to A, get help in identifying what the root cause of that afterburn was, and B, also look at design modifications that they could implement in their upcoming turnaround to mitigate the extent of afterburn. So if you look at the animations on the right, what I'm showing you are 4 different animations, and this is of their base case operation: catalyst density, catalyst temperature, oxygen mole fraction, and CO concentration. So if you look at catalyst temperature, the second animation, I want to highlight 2 things. First, if you look at the catalyst in the dilute phase, we see relatively high temperatures, and that is generally consistent with the extent of afterburn they were experiencing. And second, if you look at the regenerator bed, you see this cold spot right here. That's where the catalyst is entering from the spent catalyst distributor. And you can also see that it's not mixing in very well in the regenerator bed. If we look at the third animation, what we're seeing here is oxygen mole fraction. And if you look at this animation for a while, what you'll see is that the combustion air is kind of preferentially bypassing along the right-hand side of the regenerator. And although I can't show you the internals, what we have is the spent cat distributor enters from the right-hand side of the regen and discharges on the left-hand side where I showed you earlier. So what's going on here is the combustion gas, it's finding combustion air, it's finding a bypass channel at the bottom of the spent cat distributor and making its way into the dilute phase. Now, if you look at the fourth animation, and this is CO concentration, what you're seeing here is that we have very high CO concentrations around the discharge of the spent cat distributor, right? And that's not mixing very well within the entire bed. In fact, you see high concentrations along the left-hand side of the regenerator, and that's penetrating into the dilute phase. So that CO is reacting with oxygen to result in the afterburn that they're experiencing. So once we identified the root cause, we studied many different design options. And the most promising one was implemented in their upcoming turnaround. After the FCC came up from the turnaround, they did experience a significant reduction in the extent of afterburn. So this highlights what I'll call a typical regenerator case study using Barracuda Virtual Reactor. So finally, I want to transition back to the stripper standpipe troubleshooting example I showed you earlier. What the refiner felt is that the loss of fines did originate in the regenerator. So again, they came to us for help in understanding what the root cause of that was and to evaluate various design options. So we did verify, and that was consistent with what they believed, that this fines loss was due to excessive elutriation and cyclone loading. And where's the refiner today? They're trying to understand if the circulation issues should be addressed through changes in the regenerator design and operation, or should we implement the modifications to the stripper that we showed you earlier. And so finally, before leaving the slide, what I want to say is that at CPFD, we are continually refining our code capabilities. And in this case, we've been looking at the drag. What we want to make sure is that we can quantitatively capture the extent of elutriation coming from the dense bed, from the bed section of the regenerator into the dilute phase. So again, we are continually refining our code capabilities. So let me now shift into our next focus area, and that is the FCC riser and feed zone. So in the riser, the fluidization regime spans from dense phase to dilute phase flows. So you get dense phase flows at the bottom of the riser, let's say below the feed zone, and very dilute phase flows at the top of the riser. And to model a riser, we have to account for multiple effects. And that includes feed penetration, heat transfer, dispersion, and reaction. And the riser, and especially the feed zone, has been an area of interest as of the last few years. So to support this, CPFD has released a new liquid feed and vaporization feature back in 2019. And so I'm going to touch on this in the next few slides. So let me review some critical riser features. In the upper riser, we study catalyst holdup and contact time that supports reaction. We study the effectiveness of catalyst contacting. So it's not just enough to know the amount of catalyst in the upper riser. We have to understand the effectiveness of the contacting between the vapor and that catalyst. We study the degree of backmixing and how all these affect overall performance. If we look at the feed zone, we study feed penetration, the intimacy of contacting between the liquid feed and the catalyst, heat transfer and vaporization, and finally dispersion. So now let me talk about our extension into liquid feed systems. There's been significant commercial interest in extending Barracuda, the Barracuda platform, to capture liquid spray systems and specifically for FCC applications. So our clients wanted insight into the mixing, vaporization, and reaction performance. And this liquid feed model has been applied to several commercial applications that have been implemented in the field. And I'm showing you an example of this in the animation on the right. This is supporting one of our clients. They actually had an operating demonstration unit. And in this case, they were trying to design and optimize the feed zone, right? And we were assisting them in doing that. So a little more detail on our liquid feed and vaporization model. So what are the model specifications or the inputs to the model? They are droplet size distribution, spray angle and geometry. So in other words, is it a flat fan or full cone, whatever you have. And finally, momentum flux distribution. Now, all of these properties are typically provided by the nozzle licensor. And an example, if you look at the picture here on the right, this is a typical setup for testing an FCC feed nozzle. This is a air water setup with the associated laser camera. And from these sorts of tests, you get all these properties. If you look at the plot on the bottom, this is a typical particle size distribution, droplet size distribution. That is a direct input into Barracuda. So what are the model capabilities? We're able to model liquid penetration, liquid film transfer to the catalyst, vaporization and reaction, and all of this is, we also provide a multi-component feed model. So let me touch on this multi-component feed model. So when we want to model the feed zone, let's say of an FCC unit, we first have to start with a description of the feed, right? And the starting point there is generally a boiling point distribution or a SIMDIS curve. And what we do is we break the SIMDIS curve up into pseudo components that are based on boiling point ranges. So an example of that is given at this plot at the top, where I'm plotting temperature versus distillation, and this is a typical SIMDIS curve. And in this curve, what we've done is we've broken up the curve into 5 different pseudo components, each one representing a specific boiling point range. So if you look at the light end, that is MVP, normal boiling point 301C. We have NBP 371C, 407, 456, and the heavy tail, which is normal boiling point 554C. So once we have a description of the feed, we then have to model the nozzle. There's several approaches you can take here. One approach we take is, let's just say if you have a nozzle with an end cap that has 12 holes, we'll model those 12 holes by discrete injection points such that you get the desired spray pattern. Again, full cone, flat fan, whatever you have. And once we have a description of the feed, and once we've modeled the nozzle, we can get detailed insight into the penetration and vaporization dynamics of the system. So I'm giving you an example of that up here at the top, and here I'm plotting the mass fraction vaporized versus the distance above the nozzle, above the injection, for each one of these pseudo components that I've plotted here on the left. So if you look at the very light end component, NBP 301, what you'll see is that fully vaporizes at above 4 meters above the nozzle. Now, if you look at the heavy end, NBP 554C, what you'll see is even at 10 meters above the nozzle, that is not fully vaporized. And so for this particular example, the client was very interested in the vaporization dynamics of the 554C material. They thought that helped them identify coke precursors in the system. So additionally, we're also looking at non-conventional feedstocks. So we study both biomass and plastic-derived feeds. So let me touch on a case study regarding this, the feed zone. And in this specific example, we were supporting a client in the design and the scale up of an FCC-based technology. So if we look at the plot on the right, what this client was trying to do is understand how the feed zone performance was impacted by scale. So what I'm doing is I'm plotting vaporization time, and that's a percentage of the total residence time for their demonstration unit and 3 different commercial designs. So what you'll see for their demo unit, and they had an operating demonstration unit, is that the vaporization time was roughly 18%. Now, if you look at commercial 1, and commercial 1 was their, I call it their go forward design, that vaporization time increases to about 45%. So you see a pretty big degradation in performance there. So we tested several different design modifications or design options, and we finally came up with commercial 3, right? And we were able to reduce that vaporization time to roughly 25%. So a significant improvement over commercial 1. And how did we do that? We did that by focusing on promoting intimate contact between the feed and the regenerated catalyst. So commercial 3 was a design that they finally implemented and commercialized. So case studies like this, they demonstrate the utility of our feed zone model for FCC or CFB circulating fluidized bed scale-up, design, and troubleshooting. So now let me shift gears and focus on critical features of the upper riser. Again, we studied catalyst holdup and contact time, effectiveness of catalyst contacting, degree of backmixing, and how all of these affect overall performance. So at CPFD, we spend a considerable amount of time establishing the best practices for drag correlations and boundary conditions, right? And how these affect density gradients and the holdup in the riser. So if you look at the plot at the top, here's a good example of this. I'm plotting catalyst weight or riser holdup, right? This is the catalyst weight in the riser for 3 different cases. These cases only differ by the choice of the drag model that we used. And what you see right away is that the catalyst holdup, the prediction of catalyst holdup is going to be very sensitive to the choice of the drag model that you choose, right? In some cases, you can be up to 50% off. So additionally, the choice of the drag model will impact hydrodynamic features such as the core-annular structure. I think most of you are familiar with what that is, but loosely speaking, the core-annular structure are natural radial gradients that form in the riser, specifically with respect to catalyst density and velocity. And so an example of that is given in the plot above. Here I'm plotting particle volume fraction versus radial position for 2 different drag models. And what you'll see here is you'll see very large qualitative differences. So if you look at drag 1, that is a much more typical core-annular structure. So again, these hydrodynamic features are going to be very sensitive to the drag model that you choose, which is why we spend so much time in developing these best practices. So if you look at the plot on the right, the animations on the right, what I'm showing you are particle volume fraction for various cross sections in the riser. Let me just draw your attention to the one at the top right. So what you're seeing here, and again, this is particle volume fraction. You're seeing what I would consider to be a typical core-annular structure. So on average, you see a relatively dilute core with a denser region along the wall of the riser. So here you're seeing the corresponding particle velocity plot, again, particle velocity versus radial position. And again, you see this sensitivity to the choice of the drag model that you use. Drag 1 representing a more typical or yielding a more typical core-annular prediction. So if you look quickly at the animations on the right, again, let's look at this horizontal cross section. And again, here you'll see a much more typical core-annular feature, very high velocities at the center of the core of the riser with the lowest velocities along the wall. In fact, sometimes they're actually negative. So in addition to being able to predict catalyst holdup and hydrodynamic features like the core-annular structure, we look at the dispersion, catalyst contacting, and utilization properties in the riser. And we do this by using embedded features in Barracuda virtual reactor, which are inert and reactive tracers. You can think of these as chemical probes that don't really impact the hydrodynamics, but allow us to quantitatively measure the extent of catalyst and vapor contacting. And let me give you an example like that of this with this final case study. And in this example, we were helping a client develop a new riser technology. This was a short contact time technology where they wanted to understand the extent of catalyst utilization post-feed zone as a function of scale. So if you look at the plot on the right, we're plotting percent catalyst utilization, and that's actually measured using our reactive tracers for their demonstration unit, along with three other commercial designs. For the demo unit, the percent catalyst utilization was actually pretty good, just over 90%, let's say 92%. But if you look at the commercial predictions, right, because of the length scale, that catalyst utilization falls off pretty significantly. So after we tested several design modifications or several design options, we came up with commercial 3, and that brought that catalyst utilization back up to just over 90%, very similar to their demonstration unit. And the way we did this was by disrupting those natural, called radial gradients in the riser. So the design focused on reducing catalyst non-uniformities and vapor bypassing. And by doing this, we were able to help this client achieve conversion targets. And commercial 3 was what was finally implemented. So let me shift gears now and talk to you about the extensions of our platform to VLS applications. So we've extended the CPFD platform beyond our traditional vapor solids applications like FCC or circulating fluidized bed units to vapor liquid solid systems, VLS systems. And the way we did this is by leveraging the existing numerical platform, allowing for an efficient extension. So we currently are able to support applications including spray systems, bubble columns, ebulated beds, among others. So we extended the focus beyond these traditional application areas where we can model thermal cracking, fermentation, hydrocracking systems, among others. And to a large extent, this was driven by client and licensee feedback, where we use Barracuda Virtual Reactor for commercial troubleshooting and root cause analysis, along with reactor design, scale up, and optimization. So very similar to the examples you saw before with the FCC regenerator and the riser. So let me touch on some work that we're doing supporting a client who is developing a new process for upgrading UMO, used motor oil, vacuum resid, opportunity feedstocks, and orphan streams. And the reason I chose this example is, well, it's a good example of a step out, a commercial step out beyond our traditional CFBs, but it also really highlights the capabilities of our liquid feed and vaporization model, right? So the visualization is really good here. So what I'm going to do is begin by explaining how this reactor operates. So the feed, the hydrocarbon feed, which usually comes along with quite a bit of water, is fed to the reactor through this lance to a spray nozzle. So the feed is sprayed countercurrent against combustion gas, which is entering at the bottom of the reactor here. So the combustion gas is supplying the heat for cracking, and the cracked products, the upgraded products, along with the combustion gas, exits the top of the reactor and goes downstream for further processing. So, one thing I want to highlight here is this is going to be a pretty challenging design. So first, you don't want this feed to over-penetrate into the combustion zone, because if that happens, the feed's going to vaporize, and part of the feed's going to crack at excessively high temperatures, and that's going to cause overcracking. So you want to avoid over-penetration. But on the other hand, you want to avoid under-penetration as well. So if you under-penetrate, you risk having droplets, unvaporized droplets, elutriate overhead, and that's going to be a coking or a fouling issue downstream. So, this is a pretty challenging design. So what I'm going to do is show you 4 different animations: temperature, steam, diesel range material, vapor phase, and the heavy tail, also vapor phase. And I'm going to show you the results for a vertical and 2 horizontal cross sections in the reactor, along with a depiction of the spray. So if you look at the temperature animation, first you'll see the flow field is, of course, very turbulent. But what you'll also see is that combustion gas tends to penetrate towards the center of the reactor at the bottom and really just kind of fights the liquid spray as it tries to exit to the top. What you'll see sometimes is that the combustion gas will actually bypass the spray along the side of the reactor and almost make it to the top. So again, the design here is pretty challenging. So if you look at the second animation, and this is steam, what you're seeing here is the water that's coming in with the feed vaporizes immediately. So water is going to be the lowest temperature component, has the lightest component in the feedstock, right? So that vaporizes immediately. If you look at the third animation, this is the diesel range component in the feed. That material actually penetrates much further and spends more time in the reactor, right, before it vaporizes compared to the water. And that vaporization, the temperature there, the boiling point is going to be about 550 F. If we look at the fourth animation, the heavy tail, that material has to penetrate much further into the reactor, all the way down to the combustion zone before any significant vaporization can occur. And in fact, some of that material actually penetrates through the combustion zone, through the feed zone, all the way down to the bottom of the reactor. Now, if you look closely, you'll also see some fine droplets. Those are being elutriated overhead, and those are generally composed of heavy tail material. So that's going to pose a significant fouling or coking risk downstream. So what I want to point out here is the feed vaporization dynamics are a strong function of boiling point range, making for a very challenging design. So today we're helping this client evaluate several different design options to be able to optimize performance. And so let me finish up this talk with a few more slides and talk to you about liquid continuous systems. So we've extended the platform to capture liquid continuous systems that include bubble columns and nebulated beds. And we've recently completed the development to support commercial applications within the last couple of years, where we focused our development through service projects, engagements, and client interface. And so we've chosen the ebullited bed hydrocracker as a focus area for platform development, validation, and as a commercial application. So let me touch on our modeling of a commercial ebullited bed hydrocracker. So the commercial ebullited bed hydrocracker was modeled using operating data and reactor and internal geometries taken from the open literature. So let me describe the way this system operates. These are relatively large reactors, roughly 12-foot diameter or greater, and over 120 feet tall. So the feed will enter the bottom of the reactor, so the fresh charge and the treat gas, and they are mixed with the recycled liquid coming down from the top of the reactor. All those mix and go through the distributor plate, and those enter the ebullited bed section, the main bed. The catalyst here is expanded roughly 50% above the rest height. Of course, here's where the reaction occurs. The vapor and the liquid exit the top of the ebullited bed, enter this vapor liquid disengager, where the vapor is disengaged from the liquid. A portion of the liquid is recycled back down to the feed zone, and the remaining product liquid and gas exits the reactor and goes downstream for further processing. So what are some focus areas in the ebullited bed? We study the vapor liquid separator design and efficiency. In the main bed, we study properties like the gas holdup and the bed mixing efficiency. And at the bottom of the reactor, the feed zone and distributor plate performance. And these are going to be very similar considerations as our other commercial applications like in the FCC unit. So let's look at the bottom of the reactor and talk about the feed zone. So here, very similar to the FCC regenerator, you have the potential for liquid and vapor maldistribution. So we're evaluating various feed zone and distributor designs on the vapor liquid distribution across the grid and how these impact fluidization properties, homogeneity, and the overall performance within the bed. So what they see sometimes for these commercial applications is that the gas will preferentially go to the outside of the distributor towards the wall of the reactor and kind of channel again along the reactor wall, with a liquid preferentially channeling up the center. And of course, that's going to have a pretty significant impact on performance. All right. Additionally, we're looking at the effect of the recycle rate on the feed zone and the upper bed. For these applications, the recycle rate is actually fairly large. So recycle ratio to fresh charge can be 5:1 or higher. And as you can imagine, that's going to have a pretty significant impact on the feed zone hydrodynamics. So if we go to the other end of the reactor, the very top, we're looking at the design of the vapor liquid disengager. So here you want high separation efficiencies to reduce the amount of gas that's recirculated into the recycle line. So we've been studying various disengager designs, including what's called flow-through pans and recycle cups. An example of that's given here. This is a flow-through recycle pan. And in this design, the vapor and the liquid go through what I'll call these bypass tubes and are discharged above the cup and above the entry of the recycle line at a height and in a manner that promotes effective disengagement of the vapor. Okay, so as I mentioned before, vapor entrainment can have significant impact on bed performance. It can be quite a problem. If you have a significant vapor entrainment down this line, it's going to come back to the feed zone and back up into the main bed. So what's going to happen there is you're going to increase the vapor volume fraction, decrease the contact time, as well as having other negative impacts. And that's going to have a very negative impact on performance. So we're looking at the impact of specific disengager designs on separation efficiency. And here's an example of that in the plot on the right. This is very similar to a cyclone efficiency curve. I'm plotting here separation efficiency versus bubble diameter. And as you would expect, the separation efficiency is going to be very sensitive to that bubble diameter. So finally, pulling it all together, we perform simulations of the entire commercial ebulated bed. And we make comparisons of the simulation to data taken from the open literature. We have a pseudo-component representation of the feed, and in this case, it's vacuum resid, much like our previous applications. We have a thermodynamic and mass transfer description for both the liquid and the vapor phases. And we also have included a reaction mechanism that was estimated from the open literature. So what I want to highlight here is the efficiency of the code. So people have used CFD to look at ebulated beds before, but because of the size of the problem, typically they're looking at just one section of the ebulated bed, either the vapor liquid disengager or the feed zone. And generally they're only looking at a quadrant of this and assuming symmetry. But here we're able to simulate the entire reactor. So we were able to simulate 1 hour operation in this specific case within about 2 days. So it's pretty efficient. And an example of that is given at the plots on the bottom. Here we're looking at the separation efficiency of the vapor liquid separator, as well as the yields versus time. And so I want to end this by saying Barracuda Virtual Reactor, it's not only a practical tool for our traditional focus areas like FCC units, but it's also become a very practical tool for the evaluation of vapor liquid systems like this ebulated bed as well. So let me conclude. I want to note that CFD is most effective when coupled with a solid understanding of basic fluidization principles. And we saw examples of that when we were looking at the stripper, dense phase flows, or the riser, very dilute phase flows. We have newly introduced features in Barracuda to capture both the window of stable expansion and deaeration times for dense phase flows that allows us to model the strip and the standpipe. We've also introduced a liquid feed and vaporization model for modeling of the feed zone of the FCC unit. We're continually emphasizing code capabilities like next generation drag models that allow us to quantitatively capture the elutriation from the regenerator bed to the dilute phase. And finally, we've extended the platform to be able to model vapor liquid solid systems like ebulated beds. So with that, I conclude. Thank you very much.
Thank you, Peter. Thank you for your presentation. There's a lot of great information right here. So just in case if you have any question, because right now I have not seen any question yet from the Slido or the chat. If you do, maybe we stay here for 1 or 2 minutes if you have any question to ask. Another option is, let's say if you have any more question for Peter, feel free to reach out to me. I'm not sure, Peter, if you have provided your contact information here. If not, I can share your contact information with the audience right here in case if they have any question down the road.
Sure, please do.
Okay, yeah, there's a question right here from Mario. The question is that how much time does it take from a start to finish to create a new FCC simulation?
Yeah, so I'll give you the typical FCC answer on that, and then I'll explain it. So it depends. For example, if we do, let's just say you want to perform a typical regenerator study, like the one I showed you earlier. It will take, let's just say you want to do a few cases. Typically, we perform a base case, like I explained earlier. That's generally done to capture the current operation and make sure we're able to capture or understand the root cause of the problem, right? And to 2 or 3 different design cases. All in all, from start to finish, I would say that process will take about 8 weeks. right? But during that 8 weeks, you'll generally get critical information about the design, but from start to finish, about 8 weeks. For risers, we can usually do it significantly shorter than that, strippers as well.
Okay, thank you, Peter. I don't see any more questions here from the chat. With that, again, if you have any more questions, feel free to reach out to me. I'm more than happy to help to connect you and Peter for further questions. So, Peter, I want to say thank you for your time today to provide such a great technical information to the audience right here. Thank you again. So, just one last thing. We're going to have another webinar next month that focuses on the FCC safety. So look out for your email, and I will send out more information about the session. Thank you, Peter. Thank you, everyone.
Thank you, everybody.